biggest new features. It lets us create highly detailed geometry. So of course, we wanted to use it. Our props and hero meshes are modeled directly in a digital content creation tool. And our artists are allowed to use whatever techniques and tools they prefer. It is then exported into the editor. And once in the editor, we rely heavily on automated generated LODs for our fallback meshes. There's nothing out of the ordinary here. It's a very common workflow that most artists are familiar with. But Fortnite has a very frequent release schedule with lots of new content each season. Especially our building system is very complex and highly customizable. So a single wall, for example, can have different looks using different texture data assets. It could be a very detailed brick wall or a simple plaster wall. So we knew building all of these variations in high detail wouldn't work with our Fortnite pipeline. So we thought a displacement pipeline is the most likely to succeed. But with displacement in Fortnite, there come some requirements. We needed it to be crack-free, we needed to maintain our modular seamless tiling meshes, and it needed to work with our building system. Scalability is very important for us. We have a wide range from mobile to high-end PCs. And also, we needed to be able to update our old assets easily. A low memory footprint and a low impact on artists was also important for us. Then we needed to figure out how we are actually doing displacement. There are two common solutions. One would be a world position offset shader, which is great because it's fully dynamic, it updates instantly, but on the downside, nanite meshes are rather slow when used with world position offset shaders. And every mesh would need a very high tessellation by default. The second solution would be to model it directly inside of a DCC tool using displacement. The great thing about that is our artists would have full control over it. But on the downside is it would be a lot of work for our artists. And once it's in the engine, it's not very flexible. And that means iterating on it would be slow. So neither of those worked for us. We needed something that's in-engine, lets us quickly iterate, and has a low performance impact and a low memory impact. Then we had to solve the most common problems with displacement. If you do displacement on split vertices, you get cracks in the mesh. If you do it on an average normal, you get a distorted mesh. It's very difficult to UV unwrap, and it breaks modular seamless tiling meshes. We needed something like this, which is a mixture of direct and indirect displaced surfaces, with no splits in the geometry, and we maintain a clean tiling mesh. So we started out building a displacement prototype using Houdini. We generate a mask that determines which words are direct and which words are indirect displaced. Then each word that is indirect displaced looks up the distance to each other word that is direct displaced. And if it's in the same distance, it will copy the displacement vector from the direct to the indirect. This gives us the clean crack-free mesh that we wanted. This was a great proof of concept. But sadly, we don't use Houdini engine with our editor Fortnite builds. And our environment artists don't really use Houdini itself to model the environment assets. This meant this workflow would be rather slow. Around this time, a new feature called Geometry Script was brought to our attention. And with the help of our engineers, we were able to recreate the Houdini script inside of Geometry Script, inside the engine. And it was actually great. It was really fast, and our artists were able to get started making prototype assets. But still, this involved quite some manual labor, and it was not the workflow we wanted. We moved all of this to C++ code, and Fortnite already uses a texture data-driven system for all our destructible buildings. This lets us blend up to 4 texture sets on a single asset in a single material element. All we did was we used this texture data asset and added another slot for displacement maps, and a value for magnitude and a center bias offset. This allowed our artists to only create the low poly meshes and the displacement map, and then procedurally generate in editor all the high detail meshes using up to 4 displacement maps on a single asset. This system allowed us to optimize it even further. It only generates the minimum amount of unique meshes needed. Then our engineers added adaptive tessellation, which reduced the vertex count of our displaced meshes by a lot and reduced the overall memory usage. This is all handled under the hood. And our artists don't even have access to the high detail mesh in editor. The high detail mesh gets stored directly in the DDC and can be easily removed from platforms that don't even use Nanite. All of this lets us create these incredibly high detailed environments with a rather low impact on the artist's workflow. Next, we needed to figure out how to build trees and foliage with Nanite. Our current trees were one of the most expensive assets in Fortnite. So we knew this is going to be challenging. And previous Unreal Engine 5 demos had no trees or foliage at all because of missing features like world position offset shaders for animation and mask material support. And in general, Nanite is really good with solid, continuous objects, like rocks, for example. But smaller, non-continuous objects cause problems, like, for example, leaves. So we had no idea how detailed we actually can go with these trees. And we wanted to go from these to something like this, which was our prototype map. We started about 1 year before shipping Chapter 4. And we used the trial and error approach. We built lots and lots of trees, different types of trees, but mostly we focused on a single broadleaf tree. It was more important for us to have lots of variations of the same tree that we can easily compare to each other. We built any variation we could think of, from masked leaves to opaque leaves. Each leaf modeled was as cards with masks, and various detail from 6 million words down to 50,000 words, and various materials with different costs. Then we started profiling. We made a little blueprint that let us switch between all of our trees at runtime. This made it possible to profile everything at the same time and get data we can compare directly to each other. And we learned a lot from this. So what did we learn? Opaque materials render way quicker than any of the masked materials we tried. World position offset shaders work now, but they're expensive. And for the average density of our trees and overall performance, we had a budget of 360,000 words per tree. And that's actually not that much when you consider you have to model each leaf without the use of an alpha mask. Even so, we now had on the trunk and the leaves our opaque material. We found out that still splitting it up into 2 material elements is faster than using a single material element with a more expensive shader. And even so, we don't use masked materials anymore and don't have a masked material overdraw. Nanite has its own material overdraw problem, so keep that in mind when you build your trees. Shadow proxies can help close up this performance, but in a distance, they don't do much because Nanite will target about the same triangle count for the proxy mesh as for the real rendered mesh. And finally, when you model trees this detailed, definitely use a procedural modeling tool that's made for that. Each vertex counts with these trees. Our trees are mostly built with single leaves using about 8 to 10 words. But we use a few bigger clusters that have 30 to 38 words. We use them only in occluded areas just to fill in some density. Even so, they are higher in detail. They're actually safe on the overall vertex count of the trees because you don't have to spawn as many single leaves. And in total, we spawn around 30,000 leaves on one tree. Then we needed to optimize our world position offset shader for the animation. Our old pivot painter script was way too expensive for these trees. We needed something very simple without complex calculations inside of the shader. Our approach to that was using more lookup textures. These lookup textures were created in a Houdini script. The Houdini script takes the hierarchy that was created in the modeling tool, converts it to a skeleton, and then we run a vellum solver on this skeleton to generate the animation. This animation is then transferred back to the tree using UV mapping and the baking of the animation lookup textures. is a very similar approach to our old pivot painter script. But instead of storing the pivots, we store the animation directly in the texture. This system is effectively manually GPU skinning with a one bone influence. And we bake out 4 textures with this, where U is the animation timeline, and V is the mapping of each branch. And all of these 4 textures give us all the transforms we need to animate our trees. And the result is really high detailed trees, where each leaf is modeled, and we have nice animations on them. But that comes at a higher memory cost due to the uncompressed HDR textures we need. Sadly, we also need to sacrifice individual leaf movement with this system. And it's definitely something we want to improve in the future. Our trees also don't react to the physics field. And our animation is currently rigid. And we would like to soften this out a little bit by using at least a 2-bone influence. Now that we know how our nanite trees are built, we also know it's exactly the opposite from how our old trees were built. And we still need our old trees for platforms that don't support nanite. This means we have twice the work for each tree. But it also means we're breaking a key feature of nanite, which is a continuous LOD chain. So we needed a custom setup for this. We added the possibility to import a custom fallback mesh into a nanite mesh asset, into a single asset. And this can be easily switched at runtime depending on the detail level. And because these 2 meshes are so different, we also needed a unique material for each of those. So we added the possibility on each material to add a nanite override material to it that is then only used on the nanite mesh. Then we had the idea that in theory, nanite meshes render way faster if they all use the same material. It needed to be a single shader, no use of material instances or anything. This was rather hard to pull off, but we managed to do it by using a blueprint that automatically converted all of our trees from a 2-material setup per tree to a single material for all of our trees using UDIM and array textures. Sadly, this didn't turn out as we thought. It was actually way slower. And yeah, because of the higher shader cost. But something good came out of this. We now had a blueprint that can run geometry script on all of our trees, and we used it as our pipeline tool. This tool automatically merges the nanite and the non-nanite mesh from separate assets into one asset, and then takes the collision from another separate asset and merges it into this asset. On top of that, it also automatically bakes the imposter using a modified version with geometry script. Even so, the imposter is only needed on the fallback mesh. The nanite meshes don't need an imposter anymore. And being able to batch process all of our imposter bakes saved us so much time. This used to be days of work, and now it's a matter of a click of a button. Then we moved on to figure out grass and smaller plants. We used the same approach as for our trees. We built lots and lots of variations, and we did a lot of profiling. We had a little Houdini script that let us procedurally generate grass meshes with different details and looks. And we pretty much came to the same conclusions as for the trees. For a grass cluster of about 150 centimeters in diameter, a vertex count of 1,200 verts worked well for us. But we still needed distance culling. And because vertex shader is again expensive on grass, we needed to disable the vault position offset in a distance. This meant we couldn't use our old system of fading out the grass in the distance using a vault position offset shader. So we needed to switch that to a pixel shader. And we fade out our grass by matching the color of the terrain and the normal of the terrain. Each blade modeled is again way faster than any cards with masked materials. And low nanite overdraw is even more important than for the trees. As you can see in the overdraw visualizer, when you have rolling hills of grass, it adds up very quickly with the nanite overdraw. Then we had to again optimize our vault position offset shader for the animation. For all grass and small plants, we use a single generic lookup textures with a baked offset in it. This doesn't look as good as a real rotation, but it's very cheap. We also optimized our wind speed and noise textures. In the red and green channel, we store a directional noise for the wind. And in the blue channel is an intensity noise. Then we store the wind speed itself as a MIP map. This allows us to blend between different wind speeds just by blending between these two MIP maps. And the result is really high detailed grass, and where each blade is modeled, and we have nice animations. Fortnite is a few years old now, and we have lots of legacy content, and this needed to be updated. In general, non-nanite meshes render slower than nanite meshes, even with the same vertex count. And especially when virtual shadow maps are enabled, non-nanite meshes render way slower the larger they are. But nanite still has some limitations, like for example, per instance, vertex colors are not supported, and some materials are not supported, like translucency, for example. So based on these criteria, we made an editor utility blueprint script that we run on each of our maps and find all the meshes that we can automatically convert to nanite. With Lumen, we had for the first time realistic global illumination in Fortnite. But our content was not made for that in mind. With Lumen, we have a much higher range of exposure from dark interiors to bright exteriors. So we had to update all of our emissive materials. We used the inverse eye adaptation node to make our emissives independent from the exposure. That way, they always stay the same brightness. The same can be done with light itself, using the inverse exposure blend feature. This is great for lights that are used with gameplay and always need to be the same brightness, no matter what the exposure is. Beautiful lighting often doesn't line up with what's needed for gameplay. Player visibility is very important. And we used local exposure to balance dark interiors and bright exteriors. And then we added a little bit of lumen skylight leaking to it to avoid any pitch black areas. The bright and vibrant colors in Fortnite required us to have more control over the global illumination. For example, we had very extreme green bounce light from our landscapes. To fix this, we used the ray tracing quality switch replace node in our landscape material, and we desaturate the base color just by a little bit, and that got rid of the green bounce color. The great thing about this technique is it can be used the other way around. So it lets you light a scene much more than the surface would suggest. So here you can see a neon sign. On the right side, it emits much more light than on the left side. But the emissive itself is not blown out. But be careful with this technique. It doesn't affect screen space traces. So you want to avoid too big of a mismatch between the two. Now that we had this amazing lighting engine, we needed more control over it. And our old time of day system was very limiting. It only had a linear interpolation between 4 presets, and it was rather difficult to preview, and it has a very complex interface. So we switched our time of day system to a sequencer-driven system, which was great because we had full control over each second of the 24-hour day cycle. And for scalability, we were able to have a separate sequence for each platform. This allowed us to tweak the lighting exactly as we wanted it and needed it on each platform. This was great. We had finally instant feedback of the lighting we are creating, and it was a solid foundation for future improvement. We also got some quality of life improvement, like for example, the in-viewport controls for time of day. But on the downside, this requires a lot of keyframes. It can be rather challenging to manage. And sadly, the system is a little bit slower in performance than our old system, but it was definitely worth it. In the future, we want to improve on this system and add subsequences for weather and limited time events. We also want to have a local volume support, and in general, we need to improve how editing large amounts of keyframe and sequencer works. Thank you. Thanks to the team. This concludes the first part of the talk. I'm handing it over now to Jamie for the second part of the talk.
Hi, I'm Jamie Hayes, Senior Rendering Programmer at Epic Games. I'm going to cover the improvements we made to UE5's next-gen systems and the challenges we faced bringing them into Fortnite Chapter 4. First, I'd like to talk about the work we did to integrate Lumen, UE5's real-time global illumination and reflection solution, into the game. Let's start with how Lumen was ultimately utilized to improve the visuals in Fortnite Chapter 4. In previous chapters, only distance field ambient occlusion was used for ambient lighting, causing interiors to feel cold as blue skylight leaks into the buildings. In Chapter 4, Lumen calculates global illumination at high quality, adding back the warm sunlight bounce and detailed indirect shadows. In earlier versions of Fortnite, reflections on next-generation consoles were limited to screen space reflections. This effect is limited to reflecting what's on screen and only provides good results on mirror-like surfaces. Lumen reflections provide accurate ray trace reflections on glossy surfaces, rendering metals and smooth materials correctly, even when they are indoors. Reflections on the water are sharper, and they extend all the way to the edges of the screen. We had to face some challenges getting Lumen to scale and fit the needs of Fortnite. Our previous showcases of the tech were well optimized, but were done so to meet a 30 FPS budget. For Fortnite, we were targeting 60 FPS on next-gen consoles, giving ourselves a modest 4 millisecond budget for GI and reflections together. After some early tests, we determined that Lumen software ray tracing was a better fit over Lumen's hardware ray tracing on consoles to make it our budget due to its lower tracing costs. However, Lumen hardware ray tracing is still used on PC. The approximate nature of software ray tracing introduced several challenges. The coarse and opaque nature of the global signed distance field presented some over-occlusion issues with the trees and foliage. We developed a new stochastic way to intersect the SDF, where a choice is made at each step of the ray march whether or not to intersect. This more accurately models the aggregate nature of the canopy. Lumen's software ray tracing also adds detail to the GI with screen traces. However, aliasing could be observed when these screen traces hit grass blades. We solved this by skipping screen trace hits when they hit foliage. Another problem we faced was that the lighting on objects reflected in the water was too low res. We were sampling this lighting from a voxelized structure generated from a higher resolution surface cache stored for each mesh. To resolve this, we developed a reverse lookup structure that allowed us to sample the higher resolution surface cache directly. One artifact we had to fix was streaking that would occur where screen traces are interrupted by foreground pixels. In this scenario, we fall back to Lumen software traces to continue the trace, which could result in a color mismatch with its neighbors. To resolve this, we sample screen colors at points where a ray is hit on screen and reduces the mismatch. We also made improvements to the noise of our global illumination. Because Lumen GI downsamples heavily in order to fit into budget, the resulting noise can be more noticeable, distracting from the game experience. We were able to reduce noise greatly by integrating NVIDIA's spatiotemporal blue noise, a technique that pre-optimizes noise patterns to cancel out quickly when accumulated over multiple frames. This gave much cleaner indirect lighting without requiring any additional rays to be traced. Now let's talk a bit about what we had to do for performance to meet our 4 millisecond budget. As I mentioned before, Lumen GI scales quality down for 60 Hz by heavily downsampling, down to 1/16 of a ray per pixel. This tends to be less temporally stable and can introduce noise in darker areas. Paul showed us earlier how skylight leaking was added to help illuminate darker areas. This also served to help to hide GI noise in dark indoor locations. Another sacrifice we made for 60 FPS was to scale down the quality of reflections. Reflections are reduced to half resolution except on water. Also, we added a separate roughness cutoff parameter for foliage, resulting in fewer dedicated reflection rays and relying more often on Lumen's rough specular approximation for this shading model. The difference was not very noticeable and saved us upwards of 2 milliseconds. Lumen's processing is composed of many interdependent GPU dispatches. This results in a lot of GPU time spent in synchronization when performed in line with other graphics work. On top of that, software ray tracing threads retire in varying lengths of time, causing the dispatch to have a long tail that leaves the shader cores largely underutilized. By putting Lumen's dispatches in parallel with graphics work on async compute, we clawed back about 0.8 milliseconds of GPU time on next-gen consoles. And this is what that looks like in pics. On the top, you can see the graphics pipe, and in the bottom, you see Lumen's many dispatches running in parallel on an async compute pipe. Next up, I'm going to cover how our team helped update the geometric detail of Fortnite Chapter 4 using Nanite. At the time we started on Chapter 4, Nanite materials were missing support for a few things: world position offset, pixel depth offset, masked opaque, and two-sided. This is because Nanite's rasterization was fixed function, meaning all its triangles rasterized the same way and at the same time. So what it could do fast and efficiently. However, these features require custom logic in the rasterization shader, so we need to make the rasterizer itself programmable moving forward to support these features. We set out to build an initial prototype to change Nanite's rasterization architecture to support material graph logic. We started with a simple masked material. The prototype was successful in proving it could work, but there was a long road ahead to make it production ready and efficient. We moved on to implement the new system with a couple constraints in mind. We wanted to keep the original rasterization path fast, meaning the new feature would not slow down existing content. Basic programmable rasterization should only be marginally slower than the fixed function version, and we also wanted to continue to perform instance and cluster culling work only once for simplicity and speed. The initial prototype was hard-coded to only support a single programmable material in the scene. So the next step was to add a proper rasterizer binning pass that would let us support actual game scenes composed of hundreds of materials. This enabled us to test out actual content, though we knew we still had room for improvement on the performance side. Here you can see our test project, Medieval Game, in a debug view, showing a unique color per rasterization material. Though we knew early on that we wanted to leverage Nanite in Fortnite Chapter 4, there was a lot of existing content in the game at the time that prevented wholesale adoption, mostly using world position offset like these animated props. As Paul mentioned, objects such as these tended to create problems with VSM performance, so it became important for us to get WPO working with Nanite and get these assets converted. These existing Fortnite assets were quite useful for testing while we were implementing WPO for Nanite materials. Buildings were the most obvious candidate for Nanite integration, as it is already proven to handle large cities with ease. Paul showed us how artists generate assets that have detail and definition worthy of Nanite, while still providing standard assets for non-Nanite platforms. So what did we do on the code side to help facilitate their workflow? The answer is Nanite displaced meshes. This is an ad hoc offline process we created in an experimental plugin that takes their lower poly mesh and some displacement textures and generates a high poly tessellated Nanite mesh. Here you can see the original mesh prior to displacement, and here's the result after the displacement build process. These displaced meshes are functionally equivalent to their non-Nanite counterparts, but add noticeable detail to the structure. These details also really help showcase our VSM tech, as they drastically improve self-shadowing and silhouettes. While this tech solution is currently tightly integrated to Fortnite's building workflow, we have plans to develop it further to make it more approachable for licensees in the future. For grass and trees, we added support to the landscape system to be able to both spawn and manually place Nanite meshes. Because they animate using world position offset, they relied heavily on the brand new and largely untested rasterization techniques. During development, the Nanite and TechArt teams worked closely together to continually iterate on the trees and grass to get them to final quality and performance. As previously mentioned, we decided early on in this process to avoid masked materials in the final iteration. This was mainly due to the added cost of rasterization. Masked leaves and grass would tend to cause excess overdraw in negative spaces. These materials also incur additional overhead in the rasterization shaders from having to interpolate barycentric coordinates and sample texture alpha per pixel. After converting our trees to Nanite, an issue cropped up where the canopies of the trees would disappear in the distance, leaving them bare. This was due to the simplifier collapsing individual leaves down to nothing when generating lower levels of detail. To fix this, we added a preserve area option that will redistribute the surface area lost to simplification meaning some leaves drop out as well as others get larger in the distance. With the addition of this feature to Nanite, it was now more efficient to render the same tree meshes in the distance and up close, instead of the imposters we rendered for distant trees in previous chapters. Now I'd like to talk about some of the measures we took to improve Nanite's performance to meet our 60 FPS budget. While profiling the game, we noticed that all building pieces were using programmable rasterization. Building pieces in Fortnite make a wobble animation effect when hit or shot. As a result, we were always hitting the slow path for buildings in the rasterizer, and we were constantly doing the calculation for this effect, even when it was not moving. To combat this, we added a new project-level setting that allows you to enable or disable the evaluation of WPO on a per-object basis. Along with this setting, we added logic to the blueprint and code to only enable WPO for objects while they animate. This helps us detect when we can rasterize these objects using the fixed function fast path. You can see in this new visualization mode that the object is not evaluating while WPO holds still. This aerial view of the castle shows just how many objects previously had WPO enabled unnecessarily. This was especially bad for performance because the cost of another raster bin was compounded for each unique material being rendered this way. With the new logic in place, we reduced our raster bin count to usually a handful at any given time. Because most things rendered now as fixed function, rasterization was cheaper due to skipping the WPO calculation. Similar in spirit to buildings, we could see that even though the trees are constantly moving, it was hardly noticeable in the distance. So we added another per-object setting to be able to disable WPO at a given distance from the camera. When set on the trees, their clusters get divided between programmable and fixed function rasterization using the fast path when possible. The landscape geometry itself also proved to be a performance issue. It was rendering as large non-nanite pieces, causing poor VSM performance. To fix this, we created an offline build process to generate nanite meshes for the landscape pieces. Note that we haven't gone as far as creating a high-resolution landscape solution yet. The process merely just generates a nanite mesh from the landscape at its normal level of detail, and then nanite takes over the rendering. I'd like to touch briefly on an issue with WPO that we're still working on. We currently can't easily account for WPO when culling clusters. Therefore, large WPO values can cause verts to fall outside of cluster bounds, causing parts of the mesh to pop in and out when the original bounds fall out of view or are occluded. For UE5.1, we used bound scale on the primitive component to arbitrarily scale up bounds as a temporary solution to help resolve these issues. However, scaling tends to make the culling bounds overly conservative, and it doesn't handle flat objects well. Coming in UE5.2, material authors can specify max world position offset displacement on the material itself to extend the bounds only by the worst case amount of displacement. Let's move on to how virtual shadow maps were used to improve the shadows of Fortnite Chapter 4. Firstly, why did we choose VSM over other methods? VSMs produce higher quality shadows than cascaded shadow maps. They also perform better than classic shadow map techniques when rendering nanite meshes. And unfortunately, since we don't currently have a solution for ray tracing nanite at its full resolution, ray trace shadows are not a good fit. In previous chapters, our sun shadows involved various techniques. Cascaded shadow maps were used near the player with a single far cascade in the distance that was mixed with distance field shadows. The player character had its own dedicated per-object shadow map, and screen space contact shadows were added to provide high detail, even though they also added trailing artifacts. Virtual shadow maps improve the quality of our sun shadows up close and in the distance. They provide us with a single unified solution for near and far shadow alike. One of the biggest performance features of virtual shadow maps is the ability to cache portions of the shadow map that remain unchanged from frame to frame. We relied upon this feature heavily in previous demos to achieve our performance goals. These demos benefited from this because they featured a mostly static sun position and the majority of objects in the scene were stationary. However, in Fortnite, our performance suffered from page invalidations due to the amount of moving objects as well as the sun itself moving for time of day. We tried many things to continue to realize the performance gains from caching. We leveraged the new optimized WPO features to cull invalidations from objects whose WPO was disabled. This helped, but not substantially. We throttled the number of pages invalidated per frame based on priority. However, this created noticeable artifacts on page borders. We even considered rendering the trees in a base pose and then reprojecting them to their current pose to get self-shadowing. But we couldn't come up with a good way to separate the self-shadow from shadows cast by other objects. The bigger problem we'd have to solve would be to reproject the entire cache when the sun moves. The cost of reprojection itself is prohibitive, and the resulting artifacts would be too noticeable due to VSM's filtering scheme and high resolution. At the end of the day, we made the tough decision to disable caching for sun shadows, and we lowered the resolution to compensate. Without the help of caching, pure rendering performance became paramount. We emphasized a few times now that nanite objects are a better fit for VSM performance. This is because non-nanite meshes lack cluster culling, so whole objects must render multiple times when spanning multiple VSM pages. Therefore, we found large non-nanite objects to be the most costly. As I mentioned, landscape was a big offender. We still have some non-nanite objects in game, mostly characters, but they are few and small, so not as bad for performance. Since we converted so much of the scene to nanite, any nanite performance improvements in turn usually helped VSM performance as well. Here's some of the things we did to improve the visual fidelity of virtual shadow maps. One thing that we improved was the shadowing of subsurface materials like leaves. Previously, we were rendering back faces with a softer shadow as a rough approximation of light transmission. However, for leaves, the normals are bent outward to make the lighting over the leaf surface more spherical. So this would cause the lighting terms to flip back and forth on the surface of the leaf, creating inconsistent shadowing. The artifacts were not very noticeable on lower res shadow techniques with heavy filtering, but they were pretty glaring on VSM. To address this and to achieve a softer overall look in the shadow term, we implemented an alternative subsurface shadow mode that uses a single term that includes the rough transmission falloff, regardless of the shading normal. Additionally, we arbitrarily widened the shadow filtering cone based on the material opacity to give the impression of internal scattering. Fortnite's grass features blades that are stylistically larger than life, which meant that they cast an unrealistically large shadow. In turn, the artist wanted to be able to soften the shadow term for grass to simulate transmission. VSM unfortunately can't provide this. So we decided that grass shadows were best represented using screen space contact shadows only. The high-res nature of nanite grass tends to provide good detail in the depth buffer for this technique. This allowed artists to make grass shadows more subtle while also reducing the rendering costs. The last sun shadow improvement I'd like to cover is how we improve shadows cast on the surface of water. VSM makes use of the scene's depth buffer to determine which virtual pages are required. However, the water's surface is translucent and therefore doesn't render depth. As a result, water on the shadow on the water's surface would be low res and blocky. So we added a special water depth prepass to generate the missing depth samples. Now I'd like to talk a little bit about virtual shadow maps for local lights. Local lights such as lamps and ceiling lights in Fortnite received an automatic quality boost just by enabling VSM. It provided higher detail with fewer biasing artifacts. It also gave us more realistic penumbras as VSM makes use of the source radius light parameter to achieve shadows that are sharp at contact points and soft further away from them. Unlike with the sun, shadow map caching works well for local lights in Fortnite. They are often immobile with relatively static geometry surrounding them. Additionally, it's not as important to update them every frame since the visual impact is much smaller. A couple of optimizations were made to help out our local light shadow costs. Firstly, we categorize certain lights as being distant when their area on screen fits within a single VSM cache page. This enables us to render these shadows using faster methods. We also throttle updates to these shadows and rely on their cache, even when objects inside the shadow have moved. Secondly, we made some improvements to our one-pass projection mode to make it so that local lights render in a single pipeline draw call, instead of being interleaved with shadow passes. This significantly improved the performance of small local lights. Lastly, I'd like to cover how Fortnite Chapter 4 makes use of temporal super resolution, UE5's solution for anti-aliasing and resolution upscaling. Fortnite has a lot of pre-existing content, and it's important to maintain the quality of that content without artists needing to revisit it. With that in mind, we wanted to make sure that the art team was minimally impacted by the limitations of TSR, and we aimed to let them focus on creating new art rather than migrating previously authored art, while not regressing on detailed nanite content. With Fortnite targeting 60 FPS, TSR was no exception in needing a diet on its runtime cost. Considering the performance benefit it brings by rendering at much lower resolution, we were willing to give it at most 2 milliseconds of frame time budget. However, major, surprising, and unexpected R&D breakthroughs on what existing console hardware can actually deliver allowed us to shrink the cost of TSR much further than we anticipated. We found a way to exploit the scale-up performance of RDNA 2 GPUs with handwritten interdependent convolutions. And the ability to chain many more convolutions has amazing properties that allows TSR to become substantially smarter and shave off large GPU costs that are no longer required. More technical details on this are to be published in the future. We went from 3.1 milliseconds in the Matrix Awakens demo to just 1.5 milliseconds at equal quality, which is great news for our licensees, as we can now provide them higher TSR quality levels to use at their discretion and fit their needs, while still being able to remain under 2 milliseconds. Thanks to this and other GPU savings throughout the renderer, we were able to ship Fortnite comfortably above 50% resolution on PlayStation 5 and Xbox Series X, leaving extra GPU headroom for live events that are often organized in Fortnite and can be more difficult for the GPU. On Xbox Series S, we had to reduce display resolution as well as other effects in the game to make sure that the rendering resolution remains reasonably high, on average about 68 to 75% of 1080p, to maintain enough information for TSR to converge to reasonable image quality on more GPU-intense scenes. That pretty much wraps up my part of the presentation. I'd like to take a second to thank the members of the teams whose contributions made this all possible. And at this time, Paul and I would like to open up the floor to any questions you might have. Yeah, the mic's over here to the left. All right, well, yeah?
I had one question. When you mentioned RDNA 2's changes for interdependent convolutions, was that just hardware changes, or did you actually have to change part of your code base to take advantage of those hardware changes?
We take advantage of special instructions that come in the instruction set architecture for RDNA 2 that helps us speed up those convolutions and make them shorter in time so that we can do more of them.
Could you give a quick example of like what some of those changes were? Or?
Unfortunately, I don't. I'm not the one that wrote that. Our programmer Guillaume, he's the one that normally does that stuff. He would be the one that has all the details, and at some point he'll be giving more of those details in a different talk.
Gotcha. Thank you.
Mm-hmm.
So there was great content in your talk, but it wasn't recorded here. Do you have a similar talk recorded we can look at online?
I believe this one is going to be streamed.
It was live streamed, and it will be maybe tomorrow, I think, or later today, available on YouTube.
Perfect, thanks.
Hey, Paul, it's good to see you again. For the displacement for the legacy content, I was curious if you look at displacement from the side, if you guys were able to see what happened with the warping that happens. You look at something from the bottom or top, or?
Oh, well, that was the indirect and direct displacement, right? That we added. Basically, we never have the warping because we make a mask where the sides just copy the displacement from the front, basically. So all the edgewards get displaced the same as the front. And that way we get like a hot cutoff where we have no gap.
Like even in a brick?
We have what?
Like even in a small brick?
Yeah, it's perfect. There's no gaps or anything.
Interesting. Okay, thank you.
Hi. Hi. Especially around the improvements for rendering trees without imposters in the distance, how much of this is released right now?
This shipped in chapter 4, so it's in there now. It's live now.
I mean, in the engine. In
Oh,
Unreal.
that I think has been there since 5.1, but it's definitely going to be in there in 5.2.
Great, thank you.
You mentioned the VSM's improvements for local lights at like culling them and using the low resolution. I don't know what you exactly explained, but is that shipped in 5.2 for that fast path rendering for local lights at a distance?
I believe that made it into 5.1, so I believe it's already out.
Cool, thanks.
All right, well, if there's no more questions, I guess we'll let you guys go. Thanks, everybody.